Draw the moment diagram for the beams using the method of superposition. Consider the beam to be cantilevered from the pin support at C. To solve this problem, first of all, we need to recognize the number of forces acting on this beam. So we have vertical force from the roller at B, uniform distributed load, and the moment. Therefore, three cases. Next step would be to find all these forces. Taking moment about the point C will give us By. Sum of the forces in y direction, we get the value of Cy as 7.5 kilonewton. Once we have all these, now we can draw our individual forces. To find our moment C, we simply have to sum the forces, take moment about the point C, because it's going to take much more space. I'm going to do this in here, but if you don't know how to do that, you can go back to previous videos to check that out. After all the values have been found, we can go ahead and find our shear and moment equations. All right, so once you have your free body diagrams, you can look and try to find your moment equation. In this case, or in my case, I've already found those. So for case 1, it's going to be negative 4x squared. Case 2, it's going to be in two regions separated because we have two separate regions. So it's going to be, our load equation is going to be 0, 0. Then our shear is going to be 0 and a 45.5 because constant is our By. And then we can have our moment x, which is going to be 40.5x, take away 81. 81 is our constant. Okay, and then finally our moment for third case is simply negative 18. Once we have all this, now we are ready to sum all these together to get our moment equation for the whole beam. So in this case, it's going to be negative 4x squared plus 40.5x, take away 99. And this is our region 2. For region 1, simply going to be negative 4x squared, region 1, and then negative 18. That's region 1. Okay. Now we are good to draw our moment diagram. So for our moment diagram, we're going to begin with negative 18, because when you plug value of 0 into equation 1 for region 1, we have that. And then we're going to plug 2 into our region 1 equation. And we get our value to be negative 34. Curve's going to concave downwards. Okay. Now that we have our region 2 1 done, we can start doing our region 2. For region 2, one thing we have to recognize is there is going to be an intersection at our shear diagram, which is going to give us our maximum of our moment in this case. So to find out about that, we'll have to first of all find our shear equations. So in this case, for region 1, we're simply going to have negative 8x, and for region 2, it's going to be negative 8x plus 40.5. Using the equation 2, because we are in region 2 right now, we're going to look for our x-intercept here. And our x-intercept comes up to be 5.063. So somewhere along here is where we have our maximum. This is our 5.063, and then we can have our 6 here. Okay. All right. So now question is how much is that? So we can plug that value into our equation to find that out. And that value is 3.516. And from there we know we're going to go down to 0 at 6, but we can verify that. For the second part of this problem, we're going to have to consider the beam to be cantilevered from the roller at B. To solve this, we have already found our external reaction forces, so we don't have to consider that. And now we can simply proceed to the next step, which is to draw a free body diagram of each different force that is acting on this member or beam. So just like before, we're going to have our 48 kilonewton external reaction force from the uniform distributed load, and it's going to be 48 kilonewton. And then we're also going to have moment at point B, because this uniform distributed load is also causing it to rotate, which is basically to say as a moment. And it's going to be 48 kilonewton meter, just like our earlier problem. Then our next force we're going to consider as our moment. So we have been given 18 kilonewton meter, and we're going to have the opposite of this moment at point B, pardon me. And once we have that, we can proceed to our next force, which is our Cy. So we can have the opposite reaction of Cy at point B. And then we're also going to have moment because of the reaction force. And the reaction is going to be, if we sum the forces in for the point C, we're going to have clockwise 7.5 times 4 meters plus our moment C goes to 0. So I'm assuming it to be counterclockwise. And our 7.5 is also counterclockwise. So this means when we solve for moment, we can have negative 30 kilonewton meter. And because we haven't embedded this moment equation in anywhere, I'm going to simply switch our sign so that we have a positive moment. So I'm going to make it positive, clockwise 30 kilonewton meter, just so that our life is a little bit easier. It doesn't really matter really, but if you like, you can do this. You have the option. Now once we have drawn all the free body diagrams and recognize all the different forces we have to work with, we can start drawing or writing our shear and moment equation. So for our first three-body diagram, first of all, we're going to have our load equation. It's just simply negative 8 kilonewton meter. Then our shear equation is simply the integral of our load equation. It's going to be negative 8x. Oh, and another thing before we proceed to the next part is there's going to be two regions for our first free body diagram. So that means there's going to be the cantilevered part, which is 0 to 2, and then we have the other part, which is also negative 8, and it's going from 2 to 4, 2 to 6. And same thing we're going to have for our shear. So our first shear is going to be negative 8x plus our constant, but our constant is 0, so we're going to leave it as negative 8x. And then for our second half, it's going to be negative 8 plus our constant, but our constant in this case is going to be 48, because we know when x is going to be 2, we're going to have our this vector here, which is going to bump our here to 48 positive from and then if we take another integral of our shear, we're going to have our moment equation, which in this case is going to be negative 4x squared, and our constant is again 0 for a moment. We're just going to begin from 0 for our first free body diagram, point to be noted here. And then for the second half is going to be negative 4x squared plus 48x plus the constant. And our constant in this case is going to be counterclockwise, so it's going to be negative 48. And the and another thing, it's going to be 48 plus, one sec, I'll show you the calculation for this. So to get our value of the constant, first of all, we know that we're going to have our counterclockwise 48 kilonewton, and then we're also going to have the value from our negative 4x squared, which I've added, and because it's negative, so it's going to get added to 48, and we can have some value. And then on the other side, we're going to have to plug our second region equation, which is negative 4x squared plus 48x plus constant. And once we plug the value of x into this as well and solve for our constant, we get our solution as negative 144. For our second free body diagram, we have 0 load, 0 shear, and then our moment is simply negative 18 for region 0 to 2 and 0 for 2 to 6. For third free body diagram, we're going to have first of all our load equation, which in this case is going to be 0 for both regions. Then comes our shear. So for our shear, we just have constants, and for our constants, we know that we're going to have 0 for our 0 to 2 region, and then we're going to have negative 7.5 for 2 to 6. And then if we want our moment equation, we take an integral of our shear equations. In this case, first of all, we're going to have, for first region, we're going to have moment as constant, and we know there is no moment at the cantilevered part, point A, so we're going to have 0 for 0 to 2. And then for second region, we're going to have negative 7.5x plus a constant, and the constant in this case is going to be, so we're going to have 30 equals to And solving for constant, we get the value of positive 45, which we're going to add to our moment equation for region 2. And with that, we have all the required equations to solve for this problem. The only thing we're going to have once again, like before, like our initial equation is to find our shear, but we'll do that later, so where the shear is 0. But okay, anyway, so beginning with our moment. So our moment is going to begin at, well, I can find it again at the beam, but let's do it with equation. So, and to do it with equation, first of all, we have to add all our moment equations. So let's do that. So we're going to have negative 4x squared for region 0 to 2, take away 18. And then for region 2, we're going to have negative 4x squared, and then 48 take away 7.5 is 40.5, and then negative 44 plus 45 is negative 99. So initially, we're going to begin at negative 18. Let's say this is our point of negative 18. And then at 2, we're going to have negative 34 as a solution for moment. So let's say this is negative 34. And we're going to have second degree or second order curve. And from here, our second equation is going to take over. So for our second equation to go forward, first of all, we need to determine if there is any intersection for our shear. To do that, we have to find our shear equation for region 2. In this case, it's going to be negative 8x plus 48 take away 7.5, which is 40.5. Now let's see if there is an x-intersect. It looks like there is going to be one. And it's going to be 40.5 divided by 8. Comes up to be 5.063 or 5.1, we can say. So let's say our 5 is here somewhere, and we're going to have intersect here somewhere. So this is going to be our either maximum point, because we already have our minimum. So let's plug this value into our region 2 equation and see what value we get. And solving for our region 2 at 5.063, we get our value as 3.495. So this is going to be our maximum. And then add mark of 6, we're going to go down to 0. You can plug the value of region 2 into, you can plug the value of x into region 2 equation, and you'll get 0 for our. Draw the moment diagrams for the beam using the method of superposition. Consider the beam to be cantilevered at the end A. Solve this problem once again. We first of all need to determine our external action forces, which we found in our earlier problems. So we are using those same values again. Now we can draw our three free body diagrams corresponding to each different force on the beam. So for our first beam, which is our first free body diagram, which we're going to draw our uniform distributed load on, we need to find our moment. So our moment in this case is simply going to be 48 times 3, which comes up to be 144 kilonewton, my bad. Now we can proceed to our next second free body diagram. For this, I'm going to draw our force By, and with that, we're going to have opposite direction force at A, which is going to be downwards 40.5, and then we have to calculate our moment, which in this case is going to be clockwise, and it's going to be 40.5 times 2, which is 81. kilonewton meter. And finally, we have our C by force, which is 7.5. So at the point A, we can have opposite traction force of the 7.5, which is going to be 7.5 as well. And then we can have our moment here as well. And because A is a wall this time, we're not going to have our 18 kilonewton meter moment in this case. Cancels out. All right, so now what we have to do is find our moment equation and then our total moment equation and finally solve for our moment diagram. For our moment equation, we have negative 4x squared plus 4d8x take away 144. Moment for equation to our free body diagram number 2 is negative 40.5x plus 81. And for region 2, for the same free body diagram, it's going to be 0. And finally, for our third free body diagram, and finally, for our third free body diagram, our moment equation is negative 7.5x plus 45. Now we can add all these together to get our final moment equation. Now that we finally have our moment equation, we can draw our moment diagram. But before that, we know for sure there is going to be maximum moment once again. And we know in shear diagram, we're going to have intersection somewhere. That point is our maximum moment location. So to find that out, we have to first of all get our total shear equation, which in this case is going to be negative 8x. And actually we need it for region 2 only, so we don't even need to find region 1. So what I'm going to do is straight up focus on region 2. So it's going to be negative 8x, take away 48.7.5, comes up to be positive 40.5. And now our x-intercept is going to be 5.0625. So let's say 5.625 is somewhere here. And so our intersection is somewhere along this point. Okay, so now to start, we're going to begin with our moment. So we're going to begin with negative 18. And then at a 2, we're going to have negative 4 times 4, negative 18, gives us negative 34 at a mark of 0.2. At 2, curve is concaving downwards. And then from here, we're going to plug the 5.0625 into our second region equation, and we should get our maximum moment. And this comes up to be positive 3.516. Curve is going to concave downwards again, and at mark of 6, it's going to come down to 0.